Okay, so if we have a cue ball that's rolling straight toward the 8 ball, and it hits in a perfectly straight line, what's going to happen?
The velocity of the cue ball is not when the 8 ball would start. Because that is fast.
Okay, so if the cue ball was going 10 meters per second and the 8 ball is going 0, then afterwards,
The Q will be 0, the A will be 10.
They switch velocity.
very good. The cue ball would be 0 and this would be 10 meters per second. So it's just going to transfer the momentum straight over and you have that. What would happen if the cue ball is coming and it hits the 8 ball when the 8 ball isn't in a perfectly straight line?
It's gonna go like this.
Okay, so the 8 ball is going to go swing over that way,
Yeah.
and the cue ball would go
Wait.
this way. And what we're going to find is that the cue ball afterwards and the 8 ball afterwards will always form exactly a 90-degree angle.
Yes.
And it forms a 90-degree angle not because everything does it like this, but everything that has identical masses like pool balls does. So when pool balls have identical masses, then they will bounce off like that and we'll get exactly a 90-degree. Now, what that tells us is, hey, the momentum before, all the momentum before was in the cue ball, and then the momentum, this is before, it shouldn't have the prime mark back. Okay, so the momentum before it has to equal the momentum afterwards, but before it's all in the cue ball, afterwards we have 2 balls. So if we head to tail the ones over here, they should equal what this one was before. So if I take the cue ball prime and I head to tail it with the 8 ball prime, that should equal what the cue ball was beforehand. Does that make sense?
Yeah.
Okay, so the total momentum before still equals the total momentum afterwards, so the before equals the afterwards. Now, what fits on here is not the velocities, but the momentums, because momentum is what is conserved. But since the masses are the same here, what we're going to find is if we think of the initial angle that the cue ball was coming in, okay, so the cue ball was deflected at a certain angle, and the 8 ball was deflected at a certain angle, and again, we know those add up to 90, they're going to be complementary angles. So if I know this was the cue ball angle, then this angle has to be the 8 ball angle. Right? In our little right triangle. And again, we know that these always make a right triangle. So you look at this and you say, hey, compared to the initial momentum, this is the which side for the cue ball? Adjacent side. And for the 8 ball, this is the adjacent side. So for both of them, it's the adjacent side. So we would want to use cosine. So we're going to say, hey, the cosine of the angle times the hypotenuse, which was the momentum coming in, so that was the cue ball coming in, is going to equal the cue ball coming out. And the same thing's going to work for the 8 ball. The cosine of the angle times the cue ball is going to be the 8 ball coming out. But again, this is going to be momentum. But since the masses are the same, what we're going to find is, hey, if this is momentum, this is really mv and this is really mv, but since it's the same m, the m is going to cancel out. And since the cue ball and the 8 ball also have the same m, then the m is going to cancel out. Which means no matter which one we do, if we do the angle that corresponds with it, which again are really these angles and this angle, the velocity coming out is always going to equal the velocity coming in times the cosine of the angle of its deflection. Now, will this work for anything? No, this only works when masses are equal. So if the masses are equal, then the math is super duper simple. You look at that and you say, well, that's going to be really easy to plug into. Yeah, it is. Now, what happens if the masses are different? what happens if we have a bowling ball that's going toward a bowling pin? Again, we're looking down from the top. So if we look down from the top, the bowling ball is rolling along, and it's going to hit the pin, and the pin is going to get deflected off this way, and the ball is going to go off this way. So here we'll have the pin, and we're going to pretend the pin stays in a nice straight orientation. It doesn't get knocked sideways. And the ball is going to go this way afterwards, so this would be after and after. To do this, we need to know some things like, okay, the mass of the ball would be like 8.93 kilograms, and say it's going 2.47 meters per second. And then afterwards, it's only going 1.92 meters per second. What we want to know is how fast and in what direction is the ball going. Well, again, what is it that gets conserved in the collision? Momentum. So it's not going to be velocities, it's going to be momentum. So every time we put a drawing out here, we want to make sure momentum numbers are on it and not the other thing. So momentum is really easy to calculate. P equals mv. So I have an m, I have a v, I multiply these two together and I get, I'm thinking a number, 8.93 times 2.47. Yeah, so we get 22.1 Newton seconds is how much momentum we had before the collision. Why did I not calculate anything for the pin? It wasn't moving, so it has no momentum. So before the collision, all the momentum's in the 8 ball, and this is the total momentum we have, and it's going straight forward. So after the collision, then the total is going to be 22.1 Newton seconds going forward. But the problem is it's now contained in 2 objects instead of 1. But if we look at the pool ball, we say, okay, afterwards it was going forward and it's going to the side. Sorry, I didn't include an angle. Let's include this angle is 17 degrees. So it's going forward and it's going off to the left. Well, if it's going forward and off to the left, we can break up this triangle very easily. But I don't use 1.92 here, I need to put a momentum number. So what would be my momentum over here? Again, we go up to P equals mv, it's still the same m that it was before because it's still the same ball. If we had switched to the pin, we'd be different. So now we have this traveling at the new speed. So 8.93 times 1.92. Yeah, so now we have 17.1 Newton seconds. So now we can break this apart and we can say, hey, this sideways part is going to be the opposite side, so I'm going to use sine over here, and this side is going to be the adjacent side, so I'm going to use cosine over here. I get 16.4 over here. And I get 5.0 over here. Whoops, not in seconds. Any questions so far? Now, we said, here's where we get to the physics. We said the total momentum going forward before was 22.1, so the total going forward after still has to be 22.1. But here we're only accounting for 16.4 because the pin is also going forward and off to the right. So how much must be going forward in the pin? That's going to be the missing momentum. So we have 22.1 going forward before, and now we can only account for 16.4 of it. So if we subtract that out, we find we're missing 5.7. So we're missing 5.7. Now, is it really missing? No, it's in the pin. So the pin going forward must be 5.7 newton seconds. Now, how much of the bowling ball's momentum originally was going off to the side? Say none. All of it was going forward, none of it was going to the side, but afterwards we have some momentum going over to the side. So here we have 5 newton seconds going to the left, so how much must we have going to the right? This also has to be 5 newton seconds because if I had nothing going to the right or left originally, the right and left afterwards have to cancel each other out. Because again, the total momentum before has to equal the total momentum afterwards. So these two are going to cancel each other out, and these two together are going to add up to what this one was originally.
So you even need to know the mass of the.
We do need to know the mass of the pin eventually, and let's make up our mass of our pin. Realistically, a pin is probably about let's say it's 0.897 kilograms. That's probably pretty realistic for a pin. So that would come in handy in the very, very end step. But the physics of it was right there. The total forward is still the total forward. The total to the left has to cancel to the total to the right because initially we had nothing going left or right. There's the physics. Now we got to get back to the math. And so the math is super simple. I say, hey, look, this is a nice right triangle. I know 2 sides. I'm looking for the hypotenuse, so I just need to.
Oh, we know you.
I know 2
Pythagoras.
sides.
Pythagoras.
Thank you. So the total momentum here should be 7.58 newton seconds. And that's where you guys were getting ahead of yourself. Here, to find the angle here, I would want to use inverse tangent. And tangent, of course, is always opposite over adjacent, so we're going to have the opposite over the adjacent. That's going to give me 41 degrees. Now, why do we have to include the mass of the pin? Because, again, what we wanted was not how much momentum the pin was, but how fast the pin is going. So now we have to stop and say, okay, remembering, of course, that P equals mv. If I want to find the v of the pin, then the m needs to move down yonder. So we just figured out we have 7.58 newton seconds of momentum, and we divide by the mass of the pin. We find it was going about 8.5 meters per second, 41 degrees to the right. Isn't that fun?
Very.
So it totally makes sense though. Again, total momentum forward equals total momentum forward. Side cancels out. Then we're just doing triangle math stuff, which you're getting increasingly comfortable with. Because we keep using it over and over. That's pretty much it.